Hi everyone, I am Dr. Andrew Tehemi, and I lecture physical chemistry at the Benue State University. Welcome to my general physical chemistry lecture series, which are meant for my students at the Benue State University. However, you're free to join wherever you are. If you're my student or joining from elsewhere, please subscribe so that whenever I upload a video, you'll be notified. Today's lecture is about the Kelvin equation. Here is the lecture outline. We'll derive the Kelvin equation using a simple approach. We'll look at consequences of the Kelvin equation. Then we'll solve a problem that involves the Kelvin equation. So after the lecture, you will learn a simple way of deriving the Kelvin equation. You will learn the consequences of the Kelvin equation. And then you will learn to use the Kelvin equation to solve a numerical problem. Before we progress, let us take a quick look at vapor pressure. Vapor pressure is the pressure developed by the vapor of a liquid. So here is a cartoon of a planar liquid surface. This is the liquid surface, it's flat. That's what is meant by planar. And this is a liquid drop with a curved surface. Of course, drops are spherical because of the consequence of surface tension. These arrows around the tiny little red circles represent the interaction between the liquid molecules. So at the surface, there is a very good interaction between the molecules, as indicated by the arrows pointing directly to the molecules. If you compare that with the liquid drop, the arrows are rather pointing randomly. That's to say that the interaction of drops around the surface, the interaction of the molecules around the drop surfaces is less than the interaction between molecules at the surface of the flat liquid surface. As a result, the tendency of the molecules to escape from the drop surfaces into the air phase is higher than there is for the planar surface. As a result, the vapor pressure of the liquid drop is higher than the vapor pressure of the flat liquid surface. So if P sub 1 of G represents the vapor pressure of the planar surface, P sub 2 of G represents the vapor pressure of the liquid drop surface, then we can say that the vapor pressure of around the curved surface, the liquid drop, is greater than that above the flat liquid surface. And this is due to surface curvature of the liquid drop. Yeah, so progressing to the Kelvin equation, let us take a case of a liquid. It could be water, it could be anything, in say a beaker, and then the same liquid drop resting on some surface that represents our curved surface. This represents our planar surface. The vapor pressure of the planar surface is P sub 1 of G. The liquid in the beaker has a pressure of P sub 1 of L. The liquid in the drop has a pressure of P sub 2 of L, while the vapor pressure is P sub 2 of G. For the planar surface, the vapor pressure and the pressure of the liquid are equal. That's why this surface is flat. For the case of the drop, the pressure of the liquid is greater than the pressure of the vapor. That's why the surface curves outwardly. Overall, the pressure of the vapor pressure of the drop is greater than the vapor pressure of the flat liquid surface. Also, the pressure of the liquid drop, that's the internal pressure of the liquid drop, is greater than the pressure of the liquid in the beaker. Let us look at a case where we have series of drops. Say this has a drop radius R1, R2, and R3. What experiments have shown is that the smaller the drop, the higher the vapor pressure and vice versa. So the smallest drop will have the highest vapor pressure, followed by this, and lastly by the biggest drop rather. So the vapor pressure above a planar liquid surface is less than the vapor pressure around a curved liquid surface. The Kelvin equation shows how the vapor pressure of a curved surface depends on its curvature, that is radius. Let us consider a liquid drop, which is our modeled curved liquid surface, of radius r, as a liquid drop. Let gamma sub La represents the surface tension of the liquid. Rho, the density of the liquid. V sub ml be the molar volume of the liquid. And V sub m of g be the molar volume of the vapor. So, to be in equilibrium, the chemical potential of the inner part of the drop has to equal the chemical potential of the outer part of the drop. That is to say that the inner chemical potential has to equal the outer chemical potential. In the inner, we have the liquid phase, and in the outer, we've got the vapor phase. So if we denote this as the chemical potential of the liquid, and this as the chemical potential of the vapor, then we'll equate them. We haven't done anything wrong, because that represents what we've started with. And because these are in equilibrium, very small change in the chemical potential of one will lead to a corresponding change in the chemical potential of the other one. So a small change in the chemical potential of the liquid will lead to a corresponding small change in the chemical potential of the vapor. Let's denote the pressure of the liquid as P sub L and that of the vapor as P of G, so that we can write the chemical potential in terms of the molar volumes of the liquid as well as that of the gas, based on this expression in this red rectangle, which says the ratio of the chemical potential to the pressure at constant temperature is equal to the molar volume. So on the basis of this, we express this in terms of molar volume to have this expression, and this in terms of molar volume to have this expression. So this is the molar volume of the liquid times the small change in pressure of the liquid, which is equal to the molar volume of the vapor times the small change in the pressure of the vapor. if we assume that the vapor is perfect, that is, obey the ideal gas equation, then we can express the molar volume in terms of the general gas equation. We do that in equation 5, where this represents the molar volume. R is the gas constant, T is the temperature, and P of G the vapor pressure. This equation can be rearranged to this by dividing both sides by RT. When that happens, RT cancels RT on the right hand side, giving rise to equation 6. Remember, the planar surface and the curved surface both have different vapor pressures and the pressures of the liquid. This is the pressure for the planar liquid surface case in the beaker. This is the vapor pressure for the vapor above the planar liquid surface. And this is the vapor pressure around the curved surface. And this is the pressure of the liquid in the drop. So if we integrate equation 6 on the basis of these pressure limits, we integrate the left hand side from P sub 1 of L to P sub 2 of L. We integrate the right hand side from P sub 1 of G to P sub 2 of G. Then we obtain equation 7 on that basis. Of course, these are constants, so we factor them outside the integration. Now, if we carry out this integration, we obtain equation 8. We take the limit, the pressure limit based on this. We obtain equation 9. Of course, this is a constant, this is a constant, we haven't done anything with it. P sub 2 of L minus P sub 1 of L represents the change in pressure across the curved drop surface. And that represents our change in pressure, as you see there. And of course, this expands to give this expression on the right hand side. This is the pressure difference across the planar surface and the drop surface, and it equals the Laplace pressure, which is 2 times gamma LA divided by R. Also, this is the molar volume, molar mass, capital M divided by density. So if we substitute this expression for the molar volume and substitute this expression for the change in pressure, then we obtain equation 10. And equation 10 is the Kelvin equation. This equation shows that the vapor pressure around the liquid drop varies inversely with the size of the liquid drop in terms of radius. That is to say that if we have a small drop, of course the radius will be small, then the vapor pressure will be higher than if we have a large drop with a large radius, as the case may be. Let us advance this equation to cavity. A cavity in a liquid, which represents our curved surface in this case. Compare that to a planar surface. For a cavity is the opposite of a drop. A cavity is a void in a liquid that is filled with the vapor of the liquid, or simply an empty space or a bubble in the liquid. So The same thing applies. The internal pressure is greater than that of the external pressure. That is why it curves outwardly. So this is the vapor pressure of the liquid. It's greater than the pressure of the liquid itself. And this cavity has a radius of r. This is the pressure of the liquid. This is the vapor pressure of the vapor above the liquid. Of course, the vapor pressure is equal to the pressure of the liquid. So for a cavity in a liquid, the external pressure of the liquid, P sub 2 of L, is also less than the internal vapor pressure, P2 of G. And thus the radius of the curvature lies in the vapor phase. Because the radius of curvature lies in the vapor phase, it is given a negative sign. Therefore, the Kelvin equation for a cavity can be written in this manner. Notice that the equation for the Kelvin equation is the same for the drop, the only difference being the negative sign, which has been introduced because the radius of curvature lies in the vapor phase. So what are the consequences of the Kelvin equation? Firstly, larger drops grow at the expense of smaller ones if they exist together. This is known as Oswald ripening. So I've created an animation of how what happens during Oswald ripening. You can see that the small liquid drops disappear while the big liquid drops emerge. Another consequence of the Kelvin equation is self-nucleation. If we take the case of formation of bubbles of vapor in a superheated liquid, usually at appropriate conditions, small nuclei or embryos of the new phase form in the old phase. Now the embryos continue to grow with time. So let's take these to be the small embryos. So with time, they grow big and big and bigger. Another consequence of the Kelvin equation is capillary condensation. Capillary condensation occurs when the absorption of a vapor in a capillary tube forms a liquid surface with small radii of curvature. That is, in this case, this is capillary tube. Then there is a condensation of liquid in this tube. This is the pressure of the vapor above the liquid in the tube, and this is the pressure of the liquid in the tube. This is an expanded version of this. R sub 2 and R sub 1 represent the radii of curvature, which lie in the vapor phase because the vapor pressure is greater than the pressure of the liquid. If we compare this to the planar liquid surface, where the vapor pressure is equal to the pressure of the liquid and the surface is flat. Of course, this is greater than this. That's why there is a curved the interface curves inwardly, and the pressure of the pressure of the liquid in the tube is less than the pressure of the liquid in the beaker, in this case, for the flat surface. So the Kelvin equation for capillary condensation is given by equation 12, where all symbols retain their known meaning. R sub 1 is not equal to R sub 2. There are cases where they might be equal, but in this case, we are taking a case where they are not equal. So R1 and R sub 2 are negative because they lie in the vapor phase. So if there is a numerical question that requires this sort of equation to solve, then the negative signs for the radar of curvature must be introduced. So here is a question that involves the use of the Kelvin equation. It says, given that at 25 degrees C, the density, surface tension, molar volume, and vapor pressure of an orange juice are 0.996 gram per cm cube, 58.5 millinewton per meter, 0.018 kg per mole, 100 kilopascal, respectively. Calculate the minimum volume of an air bubble forming 12 cm beneath the surface of the juice that will remain stable. Take the values of the atmospheric pressure, gas constant, and acceleration of gravity as 101,325 atm, 8.314 joule per mole per Kelvin, and 9.8 meter per second squared, respectively. Let's make a sketch of the problem. This is a bubble forming in the juice. On the bubble, both the atmospheric pressure and the hydrostatic pressure will act on it. And this is the height. That's the height which the bubble is formed below the surface of the juice. R is the radius of the bubble. So the total pressure on the bubble at the depth, P, is equal to the atmospheric pressure plus the hydrostatic pressure. This is the atmospheric pressure, which is equal to 101,325 atm, which corresponds to the same value in Pascal. This is the density of the liquid, the juice, so to say, 0.996 gram per cm cube, which is equal to 996 kilogram per meter cube. H is the depth, which is 12 centimeters, which is equal to 12 times 10 to the power of negative 2 meters. If we substitute these values into this expression, we obtain this, which is equal to 102.5 kilopascal. This is the vapor pressure that the curved surface of the bubble will have to develop. Otherwise, it won't be able to remain stable in the juice. But we can't find the volume of the bubble without knowing the radius. So we use the Kelvin equation to calculate the minimum radius of the bubble. And from there, we'll find the volume of the bubble. So from the Kelvin equation, which is given here, where P sub 2 of G is the pressure the curved surface of the bubble would have to develop, which we've just calculated, which is 102.5 kilopascal. At P sub 1 of G is the vapor pressure above a planar orange juice surface, which is 100 kilopascal. T is the temperature, which is 25 degrees C, which is equal to 298.15 Kelvin. Rho is the density of the orange juice, which is 0.996 gram per cm cube, which is equal to 996 kilogram per meter cube. Gamma sub LA is the orange juice surface tension, which is 58.5 millinewton per meter, which is equal to 58.5 times 10 to the power of -3 Newton per meter. M is the molar volume of the juice, which is 0.018 kilogram per mole. R is the gas constant, 8.314 joule per mole per Kelvin. R is the radius of the orange juice, the radius of the gas bubble, which is unknown. And we substitute these values into this formula, the Kelvin equation. We obtain this. We evaluate this bit of the equation and this bit of the equation. That gives this. We make R the subject of the formula, giving us R as -3.45 times 10 to the power of -10 meters, meter. The negative sign indicates that the radius of the bubble lies in the vapor phase. To obtain the volume, we approximate the volume of the bubble to a sphere, and the volume of a sphere is 4/3 pi r cubed. We substitute the value of r and the value of pi and obtain this, which evaluates to give 1.72 times 10 to the power of -28 meter cubed, or 0.172 nanometer cube. Thanks for watching. You can download a link to the PDF version of this lecture in the video description. You can leave comments and I'll do my best to answer them. You can suggest possible topics you want me to make videos on. Once again, thank you for watching.